In this video, we'll discuss several questions we might ask about context-free languages. And we'll find out that some of these problems are decidable and some of them are not decidable. The first question to ask about a context-free language is, can we parse it? In other words, given a context-free grammar, can we determine whether it accepts a particular string? Or this question is really, can we build a parser for all context-free grammars? And the answer is yes, we can. This problem is decidable. If you give me a context-free grammar and a string, I can look at that grammar and determine whether that string is accepted by that grammar. Context-free languages are all parsable. One thing I could do is build a parser and then run the parser on the string. What about whether the language is empty? If you give me a context-free grammar, I can tell you whether it's empty or not. Does it generate any string at all? That question is decidable too. But now, what about if I give you two context-free grammars and ask you whether they accept the same language or not? This is not decidable. So this very fundamental question is not decidable. Are two context-free grammars equivalent or not? Are they the same? Are they describing the same language? We can't in general know this. For some grammars we can see that the answer is yes. For some we can see the answer is no. But in general this question is not decidable. So it turns out that a lot of questions are not decidable about context-free grammars. Is a context-free grammar ambiguous? That's not decidable. Do two context-free grammars have any string in common? In other words, is there any string that two different context-free grammars will generate? Is there any intersection in the two languages? That question is not decidable. What about the complement language? If you've got a context-free grammar and you take its complement, is that also context-free? Not decidable. Let's start with the acceptance problem for context-free grammars. We're going to use A for acceptance of context-free grammars. And we're given a grammar and a string, and we're asked, does this grammar generate this string? And this is a decidable language or a decidable problem. Given a context-free grammar and a string, we can write a program. Okay, we can write a program that, given a context-free grammar and a string, will tell you whether that grammar generates the string or not, and that program will always halt. Another way to say that is all grammars are parsable. Okay, which means that for any kind of for any grammar that you have, we can create a parser for it, and that parser then we can run on a potential string. If you give me a grammar, I can create a parser for that grammar, and then I can run it on string W to see whether W is in that language. We also know that for some sorts of grammars, we can create very efficient parsers, and we can answer the acceptance problem very easily and quickly. Given an LLK grammar or an LR grammar, we can generate parsers that operate in order in time. And what that means, what order in means here, this is some special notation for how long a program takes to run. Essentially, n is the number of characters in the input string W. It's the size of the string that we're testing. And order in means that the algorithm to test whether that string is in the language or not is proportional, linearly proportional to the length of the string. It's not n squared or n cubed, but it's proportional to just the length of the string. A string that's twice as long may take twice as long to parse, but anything that can be parsed in order in time can be parsed efficiently. Of course, we can't do any better than that because in general we have to look at every character in the string, so we have to take at least order in time steps because we have to examine every symbol in the input string W, and that takes time proportional to the length of the string. our algorithm has to run twice as long for strings that are twice as long, because we have to look at all those characters. So we're saying here that for most common types of grammars that you might find in, for example, programming languages, we can have very efficient parsers. In general, however, the parser is going to take a lot more time, order n cubed time, basically, where n is the length of the string. So for some particularly bizarre, nasty sorts of grammars, it can be very difficult or time-consuming to determine whether a given string is in the language or not. But it's always decidable. After enough processing and enough computation, we will come up with a yes or no answer. We will not go on computing infinitely. So how can we solve the acceptance problem for context-free grammars? Well, our first idea is that we might start by trying to enumerate all the leftmost derivations. Of course, there are an infinite number of leftmost derivations, but we can enumerate them one after the other. We can do all the derivations that have one step, and then we can do all the derivations that have two steps, and so on. So we can go through all leftmost derivations, even though there is an infinite number of them. And for each one of them, we test to see whether that derivation ends with a string w. In other words, we test to see whether that derivation is a derivation of w. And if not, we move on. Of course, there's a major problem to this approach, and that is, what if w is not in the language? Okay, what if we're asked to determine whether w is in the language generated by a particular context-free grammar, and the answer is no, it's not. Well, this really bad idea here is really bad because it won't halt in that case. I've already told you this is a decidable problem, so this is not an algorithm for that, because this algorithm may not halt, or will not halt, if w is in fact not in the language. So we need a better approach. The better approach we need makes use of Chomsky normal form. Okay, so what we're going to do here to show that the acceptance problem for context-free grammars is decidable is we're going to come up with an algorithm that's given a context-free grammar and a string, and it determines whether that context-free grammar generates that string. And the first step is to convert the grammar into Chomsky normal form. You remember what Chomsky normal form looks like? We talked about it in an earlier video. All the rules have the form of a non-terminal going to either two non-terminals on the right-hand side or a single terminal. Actually, I probably should have used different symbols here, because one of the aspects of a Chomsky normal form is that the starting symbol can only appear on the left. So I probably should have said AB or some other XY or something else over here, because we can't have the starting symbol on the right-hand side. But if you can ignore that for a moment, I think you get the idea. Every rule takes a non-terminal to either two non-terminals or a terminal. We also allow the starting symbol to go to epsilon, but we have epsilon no place else. So our algorithm does this. In the first step, it converts the grammar that it's given into Chomsky normal form. And in a previous video, I talked about how that algorithm works. It was really long and complicated, but it's decidable. And so now we look at a derivation. Let's look at just any derivation. And notice what happens in a derivation that uses a grammar that's in Chomsky normal form. At every step of the derivation, the length of the sentential form grows by 1. Remember that these things in here are called sentential forms, and they consist of both non-terminals and terminal symbols. Well, because we have this rule, S goes to two non-terminals, or any non-terminal is expanded to 2, in each step of the derivation, the length of this grows by 1. So in this step, assuming this is a leftmost derivation, we expanded this S into these two S's, and the length grew by 1. So in n minus 1 steps, we have a sentential form that's of length n. And then, so if we use just these rules, we can get a string of a bunch of non-terminals, and then we have to use the other sorts of rules where we replace the non-terminals by terminals. And for each symbol in the sentential form, in this case there are 5, we have to apply one of those rules. So it takes 5 steps to replace each of those 5 symbols and get a string of terminals. So for a string of length n, it requires n steps here and n minus 1 steps here. So every derivation of a string with n symbols has exactly 2 to the n minus 1 steps. Okay, that's our key right there. Every derivation has of a string with n symbols has 2 to the n minus 1 steps in the derivation. Well, our previous approach floundered because it was generating all derivations, and there were infinitely many of them. Now, with Chomsky normal form, let's let the length of our string w be n. Okay, so we know how many characters are in w. So now what we do is we generate all derivations that have length 2 to the n minus 1. And since n is a number, that's this 2 to the n minus 1 is a finite number. There are only finitely many derivations with that many steps, right? We have finitely many rules, and we have finitely many steps, so there are only so many derivations that we can come up with. And so we just generate all derivations, and then we check each one of them to see whether it generates the string that we're looking for. If any derivation generates w, then we accept, otherwise we reject. Now this is not the smartest way or the fastest way to determine whether w is in the grammar, but it will work for any grammar and it will clearly terminate. So this shows that the acceptance problem for context-free grammars is decidable. Next, let's look at the emptiness problem for context-free grammars. Given a grammar, does it generate any strings at all, or is the language empty? This is decidable, and to prove that any problem is decidable, we have to give an algorithm. We can give an algorithm in the form of just pseudocode or in some language, or if we want to be extra careful, we can give it as a Turing machine. But either way, we have to give and specify an algorithm, and we also have to make sure that that algorithm always halts and gives us the right answer. So we have to give an algorithm that is correct in the sense that it always halts, and therefore it's a decider, and it's correct. It gives the right answer. So now let's look at this problem of whether a context-free grammar is capable of generating any strings at all. I'm going to show the algorithm on the next slide, but I'm going to work through an example on this slide to show how the algorithm works, because I think it is easier to understand with an example. So we're going to consider a context-free grammar. Here's my context-free grammar, and we're going to ask whether it generates any string at all. In other words, can the starting symbol s be used to generate a string of terminal symbols? We're going to actually answer a more general question. We're going to answer that same question not just for s, but for all the non-terminals. So we're going to ask which non-terminals can generate a string of terminal characters. So let's look at this grammar a little bit more closely. We've got non-terminals s, a, b, c, and d. And we've got some terminal symbols, w, x, y, and z. And well, it's a marking algorithm. What we're going to do is we're going to look and see which non-terminals can generate a string of all terminals. And we see that this rule right here, if we use a goes to x, y, z, we can generate a string of terminal symbols with a. So let's mark a. All right, we'll mark a there, and I'll mark a everywhere it occurs, okay, with a red line. Now let's see, does it occur anywhere else? No. Okay, so everywhere that a occurs, it's marked. A can generate a string of terminal symbols. It can also generate some other sentential forms, but we don't care about those yet. So what else can generate a string of terminals? Well, B apparently can't. It can, but C here can generate a string of terminals. So let's mark C next. So we'll mark C here and C there. Everywhere that C occurs, we'll mark C. Okay, we'll mark it there, there, and there. Okay, I think I've gotten them all. Now, what else? Well, let's look at this rule right here. B goes to CA. We know that C can be expanded to a string of all terminals because we've marked it. And we know A can be expanded to a string of all terminals because we've marked it. Everything on the right-hand side is marked. Everything on the right-hand side is either a terminal symbol or it is marked. So therefore, B can generate a string of terminals too. Now, so we can mark it. Notice that this rule right here is not enough. We know that A could generate a string of terminals, but up until this point, we don't know about B itself. So, but now we do know about B, and we're marking B. So we're marking B everywhere it occurs. Let's see, it occurs down here, and it occurs up here. Okay, and now we've marked everything except for D. And so we go down here and ask, can D generate a string of terminals? Well, no, not there. B can go to a string of terminals, but we don't know about D. Apparently D cannot go to a string of terminals. So D does not get marked. And so now we're done marking. We can look at S. Did S get marked in this process? Well, if we had marked D, then S would have gotten marked. But we did not mark D. S did not get marked. So the answer here is no. S cannot generate a string of terminals. And so this, in fact, is a grammar that is empty. The language is empty. Now we can show the algorithm, and the algorithm is pretty straightforward if we understood the previous example. The input is a context-free grammar, and it's a marking algorithm. So we're going to see a repeat loop, and we repeat until nothing more can be marked. Okay, so what we're going to start with is marking all the terminal symbols in the grammar. So I didn't show that on my previous example, but I suppose I should have marked the terminal symbols, and then that allows us to mark A. And down here, I've marked W as well. So we mark all the terminal symbols, and then we look through our rules. And every rule has a non-terminal on the left-hand side and some terminals and non-terminals on the right-hand side. And we look for a situation where all the symbols on the right-hand side have been marked. For example, we had a rule B goes to CA, and we'd already marked C and we'd marked A, so then we mark B. So when we find a rule where everything on the right-hand side is marked, we mark the non-terminal on the left-hand side and everywhere else it occurs. And we keep repeating this until we can't mark anything more. And then we ask ourselves, is the start symbol marked? And if the start symbol is marked, then we know that the language can generate something and that it is not empty. Otherwise, we know that the language is empty. And so I think I've gotten this reversed. Just backing up, if the language is empty, we want to accept. Okay? So the language is empty if the start symbol is not marked. So let me modify this. If the start symbol is not marked, then accept, and then I'll just put L sub G is empty. If it is marked, then the language of the grammar is not empty. Okay?